In this problem, we're asked to determine the horizontal force P needed to pull out wedge A. We're given the coefficients of static friction for the three pairs of surfaces in contact, and we're told to neglect the weight of each wedge. So in the situation shown, ignore the force P, that's what we're solving for. Wedge A is what is known as self-locking, that with the 3,000 pounds applied to wedge B, wedge A is not moving due to sufficient frictional forces acting on it to keep it in place. So we need to determine the magnitude of the force P shown to unlock the wedge or get it moving to the left. So this is an impending motion problem with impending motion in the to the left, and they gave us the coefficients of static friction necessary, so let's put those on here so we have them. So between B and D, I have mu sub s equals 0.2. The same between A and C. And then between B and D, in order to distinguish, they called it U prime sub s equals 0.1, since it's a different value. Okay, well, we need to solve for P, so I'll start by drawing a free body diagram of wedge A. Okay, so this is A. I know I have the unknown force P acting on it. I have a normal force acting upwards. Call that N sub 1. And I need to find the force. We're trying to find the force P when the block is just starting to move to the left, impending motion. So I know that the limiting static frictional force acts to the right, and that is equal to mu sub s times n sub 1. And I also have we also have a normal force acting on the block from B. We'll call that N sub 2, and the limiting static frictional force between A and B is the coefficient of static friction, which we were told was 0.1. Oops. (0.1) times N sub 2. Now, we're not concerned with tipping in this problem. We know the block's just going to, the wedge is just going to slide. So it doesn't really matter where we show those two normal forces on their respective surfaces. And remember that normal force, we're showing it as a concentrated force, but it's really distributed along the surface with some unknown distribution. And it's fine to show it this way, but we need to realize that we're not going to have that moment equation available to us as one of our three equations of equilibrium. So we'll have the two equations, the sum of the forces in the x equals 0, and sum of the forces in the y equals 0. And we'll use our standard reference axes. So If I count up the unknowns in this free body diagram, I have 1, 2, 3, and with only 2 equations to work with, we're not going to be able to solve for those 3 unknowns. So I will draw a free body diagram of the wedge B. I'll call that B. Show the 3,000 pounds acting on it. Show a normal force from the wall. Call that N sub 3. And B is going to move down when A moves to the left. So the wall is going to resist that motion with the frictional force 0.2 times N sub 3. And then on the bottom surface of B, I'm going to show an equal and opposite normal force that acted from that acting on A. So it'll have a magnitude of N2, but it'll act in the opposite direction of N2. And then I'm going to show an equal and opposite frictional force from what I showed on A, which is going to be 0.1 N sub 2. Now I pick up 2 more equations with this free body diagram. Again, sum of the forces in X equals 0, sum of the forces in Y equals 0. And now note that I've only picked up 1 new unknown, N sub 3. N sub 2 is already accounted for in the first free body diagram. So now I have 4 equations to work with and 4 unknowns. So I should be able to solve for those unknowns, or the ones that I need to in order to solve for P. Okay, so I'm going to start with writing equations for the free body diagram of wedge B. I'll sum forces in the Y direction. I'm going to have the 3,000 pound force acting downward plus 0.2 N sub 3 plus N sub 2. Now N sub 2 I need to break that into components, and what we have here, we refer back to the original figure. We had an angle of 15 degrees between the horizontal and the top surface of wedge A. So that 15 degrees is going to show up in both free body diagrams, obviously, and I'm going to show it on this one as there. And if that's 15 degrees, then this is also 15 degrees in here. Okay, so it's going to be N sub 2 cosine 15 degrees in the Y direction plus 0.1 N sub 2 sine 15 degrees in the y direction. Okay, and if we do that math, we get 0.9918 n sub 2 plus 0.2 n sub 3 equals 3,000. Okay, so we have two unknowns on this free body diagram. Of course, one now, n sub 2, is shared with the first free body diagram. So we're going to need to write the second equation here and then solve simultaneous equations. So the sum of the forces in the x direction for the free body diagram of wedge B equals minus n sub 3 plus n sub 2 sine 15 degrees minus 0.1 n sub 2 cosine 15 degrees. Now these can be a little tedious with the, with the unknowns and the angles. You just have to work your way through it. So I'll simplify that and I'll get 0.1622 n sub 2 minus n sub 3 equals 0. And now I need to solve those two simultaneous equations in n2 and n3, and I'm not going to go through that, but you can see here in this equation it's set up pretty nice that you can say n sub 3 equals 0.1622 n sub 2 and put that back into this equation. And when you do that, you get n sub 2 equals 2929.0 pounds. Now note that I don't really care about n sub 3. I want to get n sub 2 so that I can then take that value back over to the first free body diagram of wedge A. So now, armed with that information about n sub 2, I'm going to go back to my first free body diagram, some forces in the y direction. And now I'm going to start off with n sub 2 and quickly show where that 15 degrees is again. It's going to be here. And it's going to be here. Okay, so sum of the forces in the y direction equals negative n sub 2, which is negative 2929.0 times the cosine of 15 degrees minus 0.1 times n sub 2, which is 2929.0 times sine 15 degrees, and plus n1. I'm sorry, I should have started that equation further to the left. I'm going to stick the plus n sub 1 down here. So that's all the forces in the y direction. And I've only got one unknown there. So I can solve for n sub 1, and that equals 2905.0 pounds. Now I can solve or write the equation for, and I'll start it further to the left. Sum of the forces in the x direction, where I can finally get the magnitude of P involved here. That's going to be minus P plus, I have a 0.2 times n sub 1, and I said n sub 1 was 2905.0, plus I have a 0.1 times n sub 2 times the cos of 15, and I know n sub 2 is 2929 times the cos of 15, and I still ran out of room. Okay, so I'll put it on the next line here. Minus, I have n sub 2 times the sine of 15 in the y direction, and n sub 2 is 29.0 times the sine of 15 degrees, and I just have the single unknown P, and when I simplify all that, I have P equals 105.8 pounds. So it takes 105.8 pounds, takes a force of magnitude 105.8 pounds to apply to wedge A, that force acting to the left to unlock wedge A and get it moving to the left.